here. Okay. So, okay, I will come to your question. I will start with some problem, new problem, and we will see that whatever we discussed in the previous lecture, that will also uh, come again in this problem. Okay. So today we are going to. Am I audible?
Yes, sir.
Okay.
Yes, sir.
So I am sharing some lecture notes. Are you able to see them?
Yes, sir.
Okay. So you can see on the screen. I have drawn a rectilinear Cartesian system x and y, and this is xy plane, and there is a mass m which is attached to the origin, and it is attached through a spring, and this spring has a spring constant of k, which you can assume anything. I have kept it as a 3, and the mass of this body is 1, and the unstretched length of this spring is 3. So L naught is the unstretched length of this. That is the normal length of the spring, and that is, I have taken it as 3. And G is the gravitational constant, and I have taken approximately it as 10 meter per second square, obviously. So now what is the problem? The problem is that we have a body which is attached through a spring to the origin, and we will and there also it is acted upon by the gravitational pull along minus y axis. And if you just disturb it from the equilibrium position, that is, you elongate it from the normal position, so there will be a spring force which will try to bring it towards the normal position. And also due to the gravity, there might be some other effect. So we want to solve the equations of motion for this system, which is easy. So we are actually building something intuition towards the MATLAB coding which we are doing. So basically, we are taking the simple problems. So it is not the purpose of today's and the previous lectures to solve some difficult problem. Rather, we are introducing that how we are going to approach the problem via MATLAB. So basically, that is the purpose of this class also. So we will solve the equations of motion numerically, and we will then simulate, or we will animate this problem. So let us, we know for that we have discussed a general idea that first we will be using constitutive laws to find the acceleration of this particle, and then we will integrate the acceleration to get the velocity. And once we get the velocity, we integrate that velocity to get the position at any time t. And then if we know the position at any time t, by position I mean x coordinate and the y coordinate at any time. So I will just I will use the plot command in order to plot x, y with respect to the time t. That will finish our problem. So I am taking this mass m, and we know that there are two forces. So this is the free body diagram of this problem. So in order to keep track in which direction the forces are acting, I have redrawn this Cartesian system here. Otherwise, FBD don't require these things. If you remember correctly, I have already told you that in FBD we only show the external forces. There is no acceleration and velocity and other things. Even there is no this position and other things. So here I am showing this position. The only reason, and I have shown it in the dot so that you will not be confused. You will not take it as some integral part of the FBD. So those which are in bold arrows, these represent the external forces. So there are two external forces on this mass M. When you stretch it, there is a restoring force due to this spring, which I have represented as Fs vector. So vector because it is a force and it might have any direction. Okay, and there is a force, constant force on this M, which is acting downwards, which is mg. Is this okay till now?
Sir.
Yeah, okay. So now also this spring, it is attached to the origin, and this origin it is attached through a pin joint. So there is no there is no restrictive force or torque which is being generated through this hinge. So it is free. If it moves this, it will freely move like this. Okay, so it is not like what we can say. It is not like a cantilever or something like that. It is not of that nature. So it freely allows this spring to move around this origin. Okay. So there is no external force acting here. That is why I have not. Oh, okay. That there is one force which obviously we will discuss as we go along, but there is no restrictive torque. So I should restate my statement. That is, there is external force being applied here, but there is no torque being applied at this hinge. So it is free to move, but it is not free to move along x and y axis. So it is restricted there. This point is restricted to origin. This is what is known as constant force, which we will discuss in as we go along the course. Okay. So basically, but here I am only interested with this mass, that is m, and there are only two forces. One is Fs and another is mg. So we basically want to find the instantaneous position of this mass m, that is r cap. So uh, I am writing this mod of r, which represents the modulus value of this, which represents the distance of this mass or the displacement of this mass from the origin, which is mod of r, and it is equal to L. So mod of r is basically nothing but under root of it is x component square plus y component square. Similarly, I am writing mod of r naught cap. That is the undisturbed length of the spring. That is L naught. Okay. So and then I am writing mod of Fs. That is the spring force. It is modulus value is Fs. These are some denotions which I have used. Now we can see that this spring force, it always acts uh, along the spring. Okay, if the spring is in this direction, this spring force will act along this line. So if this is r, this Fs will act along minus r. So the magnitude of this force Fs is mod of Fs, and the direction of that force is in the negative direction of r. So negative direction of r I have represented is minus r upon mod of r. So basically this gives us the unit vector pointing in opposite direction to the r. So this minus r upon mod of r, any vector divided by this magnitude of vector, that gives us the unit vector pointing in that direction. But I have used minus sign, so it gives us a unit vector which is in the opposite direction to the r. So this Fs is acting in the negative direction of r. And see, if this mass goes here, the spring will be somewhat like this, and the spring force will act like this. So it is not something which is constant heading in this direction. No, it depends upon where this mass is. Accordingly, r will be determined, and accordingly minus r cap will be determined, and Fs will act along through that line. So this is like and mod of r I have used it as L. So this is L. This is not L naught. There was some mistake. So don't mix it with the L naught. This is just L. So now, what is the magnitude of the spring force? So you already know when we have a spring and its normal length is L, and when we so let us shift to whiteboard. Okay, so you know that if we have a spring and we have a mass attached to it. So if this is the normal length of this spring, then if we elongate it a little bit, and this elongation, let us denote it by delta L, then we know that there is a restoring force acting on this mass, and that force, here we have called that force as Fs, and the magnitude of that force is nothing but spring constant times this delta L. So similarly, here I am using that thing. So mod of Fs, that is Fs, is nothing but delta L, which is L minus L naught times K, that is spring constant. Okay, so this is the scalar part of, or the magnitude of the spring force. Now the vector form of the spring force is, from here we can see minus Fs, that is the magnitude of F, and that is here we have calculated, divided by L, and this is divided by L, K R. So here R. So we have got the vector form of this spring force. Now we will be applying linear momentum balance equation. So now what is the linear momentum balance equation? Actually, it is nothing but the Newton's second law. So you know from Newton's second law that mass times the acceleration is summation of all external forces. So the only two forces on acting on the spring is spring force, sorry, on the mass is spring force and the gravitational force. So mass times acceleration is Fs plus mg, where we have seen that this acceleration is equal to Fs plus mg upon m. So you have to write here divided by m. There is a mistake here. So A is equal to Fs plus mg upon m. Okay. So going further, we can say that Fs, we already have calculated this Fs as minus L naught upon L K R. And G is nothing but minus Gj, where G is 10. We already, this G is simply a constant representing the value of 10. And J is a unit vector which is pointing in y direction. So our gravitation is acting along minus y direction. So I have used it as minus J. And now how we will use this in the MATLAB. So before shifting towards MATLAB, uh, anybody having any question or confusion, he can tell it. Anybody having any confusion?
When you are writing it,
RVS,
Okay, Dayan, you can go ahead, and then Mustafa will tell. Yeah.
sir, are we assuming that it will always be traveling in a sort of a circle, or it will change its length, sir, or it
Or
will
it,
form?
okay, so you are saying that we are assuming it to move in a circle. Do you think we have made some assumption regarding it?
So no, because we can also say we don't do that. It might as well
Yeah.
fall like a string. It will act as a string.
Yeah.
So
Yeah.
what actually is happening? What are the assumptions?
Okay, so you keep these things in head. So you have made one thing that we can presume it as a string, and then you should know what string is. Can you differentiate between a string and a spring? So if we
Uh,
assume that this spring is a string, so now how will you formulate that problem?
sir,
Okay,
purely.
okay. Yeah. Yeah, go ahead.
Sir, if it is a string, it will be slacking in this case. So until it's completely vertical, it will be purely like a free
Yeah,
fall. But if I'm assuming it is a spring,
yeah,
then it could be a, say, a soft spring, so that it bends, it buckles under its own, under this motion.
yeah.
So it can have a
Okay.
non-circular motion in that
So
case.
yeah. The first assumption I made was that that there is no moment acting at the origin. The assumption which I made was only for this purpose, so that there is no buckling. Okay, so there can be compression, there can be radial compression on the spring, but there can no buckling. So to make this clear, I will draw a figure so that it is clear. So basically what I mean when I said that there is no restrictive moment here being generated. So basically if this is our spring, so this spring can compress in this direction. So this spring can become this. Okay. So this spring can elongate in this direction. So it can become this. Okay. So this spring can fall down and it will be like this. Okay. But this spring can never be in this state. Like if I have this, so this spring, it will never take the shape of this thing. The thing is that I have made an assumption that there is no such torque being generated here. So that was for that purpose, and also that I am assuming that this spring has a very high stiffness to restrict its bending and other things. So it is only compressing. It doesn't show any kind of bending. Okay. So is it clear now?
Yes, sir. Yes, sir.
Okay, but your question, what if it is a string? So keep this in mind when I will show you simulation. So we will take some things to make it string and other things. You said that it is a soft spring and it is a very, so we will discuss these things. But you keep these things somewhere written so that you ask it these questions at the end if I don't answer these things. Okay. Any other question? So Mustafa, you were saying something. Yeah, go ahead.
Sir, when you are writing the Bangalore equation, sir, MA is
Yeah,
equal to FS plus MG.
FS.
So why,
FS.
why
Yeah.
what taking, sir, component of the MG along the FS, sir? MG, sir, cos theta, sir, MG cos theta.
Okay. Okay. So you are saying that that is why I have written this. This equation is a vector equation. I have not said anything. What is the direction in which Fs is pointing? I am not saying what is the direction of G, and I am not saying what is the direction of acceleration. I don't know what is the direction. That is why I am writing it in the vector form. One thing is for sure that this acceleration is in the xy plane, and this fs is also in the xy plane, and g is also in the xy plane. I don't know their direction. So this vector form will take these things into consideration automatically. That is why I am writing fs as a vector. Uh, See, you are saying that you take the component of this mg along this direction. So each point I have to calculate this theta, and then I am using the FBD or using the angle, this linear momentum balance equation in that direction. Okay. So I don't know those things. What I in general know that mass times the acceleration is fs plus mg, and I also don't know what is the direction of fs and g. These directions will be determined by these things. So this will determine what is the direction of fs. So I will put these things and they will automatically generate the direction and the magnitude of fs. Is it clear or more clear
Okay, sir.
clarification here?
Thank you.
Okay. So anybody else have any question before we shift towards MATLAB? How we are going to simulate these things? That's how we are going to solve these equations. Yeah, Rashid, and Mutawakkil asked me if I am pronouncing in a correct way.
Yes, sir.
Yeah. Yeah. Any doubt?
No, sir.
And Mutawakkil asked me.
No, sir.
Mutawakkil, are you there?
Yes, sir.
Hello? Mutawakkil, I am
Yes, sir.
speaking to you. So any doubt?
No, sir.
Okay, so let us go ahead, see how we can. So let us quickly recall and see what we have done till now. So basically, there was a problem like this. We draw it as FBD. We use the constitutive law, which was nothing but which was saying that this spring force is, there was a relation, and you should know that this relation is known as what is this known as? Yeah,
Hooke's law.
yeah.
Hooke's law.
Law. Yeah, so this is what I am. So constitute. I told you in I think in the first class that we will be using some constitutive laws. So this is here constitutive law. That is the Hooke's law. Okay. So we have this law which is relating the force to the position. Okay, L here represents the position, and then we are using the Newton's second law, which is linear momentum balance equation, and we are getting the acceleration. And once we get the acceleration, we will integrate it to get the velocity. We will integrate the velocity to get the position, and then we will plot this. So this is how we will be going. So in MATLAB, what we will basically do, so we know r dot, which is the rate of change of position with respect to time, it is velocity. And rate of change of velocity is nothing but the acceleration. So when I am saying V and A, these are actually vector components. So these will have two components, X and Y. And like in previous, we will be doing, this is a systematic way. That is why I am doing this. So we will be doing this again and again. So we define Z as R and V, so position and velocity. And position itself will have two components, X and Y. So basically this R also represents this vector, or we can say it is also a matrix which contains X and Y. And velocity in itself contains two components, Vx and Vy. So basically this mass will have two components of velocity. At any point of time, let us assume that it is moving in this direction. So that velocity will have some X component and it will have some Y component. Okay. So this Z, so basically if we are defining some variable Z, so it will have how many components? 1, 2, 3, and 4. So basically this Z will have it will have 4 components, and then each component will have some T number of values depending on how many steps we have used it in the time. But basically it will have 4 rows. First row will represent the X component of the position, second will represent the Y component of the position, third will represent the velocity in the X direction, fourth row will represent the velocity in the Y direction. And similarly, Z dot is nothing but R dot, V dot. And R dot is nothing but velocity, and V dot is nothing but acceleration. So we have expression for this acceleration which we got, that is Fs plus mg. So I will write this acceleration is as Fs plus mg, and this is the acceleration, and I will integrate this acceleration to get the velocity here, and then I will integrate that velocity to get the r. So basically we have this Z dot, we have made, so the whole purpose of till what we did, so the basic purpose was to get this Z dot. If you remember from the previous class, we were able to get this Z dot. So here also we have got this Z dot, and we will now put this to the ODE that will integrate this thing, and once that will integrate, that will give velocity. Velocity will be integrated to give the position. So now how we will be using that thing, so we will shift to MATLAB and see how we will be doing this. So as in previous, we saw that we use close all to close all the figures if there is any figure running in the MATLAB. So and then we use CLC to clear anything which is in the command window. So basically this is the command window. You can see that this much amount is there. So when the program will run, CLC will run. So this will be cleared. And then clear all. If there are some variables previously stored in the workspace, those variables will also be cleared, and then new, they will be saved as the new. So first we start with, I hope that you have saw the previous video at least 2-3 times to get some intuition and some understanding of this algorithm. So we use t, and this is the time for which we want to animate our problem, and then we use animation speed equal to 1. So these are just basically variables. T and is a variable, animation speed is a variable. T span, so T span is the time which we will be giving as input to our ODE. So ODE basically requires the time, starting time and the end time for which we are going to integrate this our function through ODE. So the new thing here is this parameters. So I will come to this parameter, but first let us assume that this is mass equal to 1, p dot k, this is spring constant equal to, this is L naught, which is initial length or the normal length of the spring, which is 3, and then this is g equal to 10. These are parameters which we have already defined here. So these things I am storing in the MATLAB as parameters. So these are basically parameters of this problem. So I can vary these parameters. That is why I have written these in this fashion. Okay. So initial condition. So what is the initial condition? So R naught. So you can see this is R. Initially, if it is somewhere here, so then this R will be called as R naught, and R naught will have two components, X naught and Y naught. So this 10 is X naught, and this 5 is Y naught. And see, I have written column. So this is a column vector. In first row, it represents the X component, and in second row, it represents the Y component. Similarly, V naught represents the initial velocity. It is not like that you are always starting with a zero velocity, but we can start with zero velocity. That is also permissible. But in general, we may have any initial velocity. So we will see how this initial velocity will affect our solution and other things. So we have initial velocity X component as 0. We have initial component of velocity as 0.1, which we can also take as 0. Let us take it as 0. So we start with 0, 0 velocity. And then z naught, which we have to actually integrate. So we are initializing that variable because we will be integrating this z dot. So we need initial value of z, and we have defined z as nothing but r and v. So this is r naught and this is v naught. So this is basically our initial condition for z. Okay, so I have written it 2 times. I don't know why I have written. So let me delete one. And okay, now the thing, the basic thing and the most important thing is this thing. So you can see here, I am writing this as function. So this is the most important thing which you have to build by yourself every time. Rest of the things will remain same for the coding, but this part will always change, and it will depend on what problem you are solving. Okay, and how you are writing the code. So what this function will do, see, it is giving us z dot. So let us see here what this is actually doing. So see, it is starting from here. It gives us z dot. So what is the z dot in terms of z? Because we will initiate z, so we know initially what is z. We don't know what is z dot naught. We don't know what is the rate of change of z initially. But if we have a relation of z dot with z, so we can find what is the initial value of z, and then it will keep on integrating, give us the new z. We will put back that into this equation to get the new z dot, integrate that once again to get. So this will keep going back forth. Okay, so we will, so see first what happens. We have some initial value of z, and we have a relation between z dot and z. So we calculate z dot initially using the initial value of z, and when we get the initial value of z dot, then we integrate it to predict the new value of z, and then we get the new value, and then we put it back into this equation to get the new value of z dot, integrate it again, get new value, and keep going like this. This is from the first class which I was telling you, that if we have a derivative, we can predict the next value of the variable. So if we have z dot, we can predict what is z next time. But initially, you have to initiate it with the z. So we should have some relationship between z and z dot. So this is the relation which we have got. And how we are using it here, see. So basically, we want z dot. This is our purpose. So we want what is z dot. And we have seen this
Sir,
z dot. Yeah.
sir, can I say
Yes.
that a relation between z and z naught is just we have to integrate the z naught so as to get z.
Yeah, you have to integrate z dot to get z. Yeah.
That is
Yeah.
the final relation between z and z naught.
What are you saying? Tell again.
That is the final relation between the z and z naught. Just we have to integrate this z naught so as to get z.
So initially, you will have initial value of z dot, and then that z dot, initial value of z dot, you will call it as z dot naught. But it is not z dot naught which you are integrating. You are actually integrating z dot.
Z
By
dot,
z
yes.
dot, I mean at any time you have the value of the derivative of z, that is z dot. You have that value, you integrate it to get the z value. Okay.
Okay, sir. Before we integrate, we have just to take an initial value of z naught dot.
Yeah.
Okay, sir.
Okay. Anybody else have any question?
No, sir.
Okay. So, okay, it seems that everything is fine. Hope it is fine. So, okay. So I was saying that the basic purpose of this function is to get z dot. That is why I have written z dot equal to. So I am actually, by this function, I am calculating z dot, nothing else. So basically, I am calculating this z dot through this function, which I have named this function as my RHS, and you will see why I have named it like so. And this function, I will give it input as z, and obviously my parameters. If I don't know what is spring constant and other things, and obviously your z dot will depend on those parameters. So I will give input as parameters and the time at which I want to calculate z dot, and obviously it depends upon the z. So these are the three inputs to this function. Once I give these three inputs to my function, it will give me this z dot value. How it will give me this z dot value? That is something
What
which
is
I have wrote here. Yeah.
what is parameter p?
This parameter p stores the spring constant value, mass of the ball, and it stores the gravitational constant. See here, mass is nothing but p dot m, g is nothing but p dot g, and k is nothing but p dot k. So why I could have also used like I could have used m equal to 1, g is equal to 10, k equal to 3, l not equal to, just I have to write it here and I could use it. But the thing is that if I use directly m equal to this, g equal to this, k equal to this, and l not equal to this here, then if I want to change something, I want to see how things will change if I change the spring constant. Then I have to change it here also. Okay. So in order that I don't need to change it here, I only need to change it somewhere at one place. I have used this as the structure. I will tell more about this, but at this point of time, keep in mind that m is nothing but p dot m, where p is storing. In order to extract the value of mass, I am taking dot of it with respect, sorry, p dot m. Okay. Uh, because if you see here, I am first defining p dot m equal. This is how we define the structure. So p is a structure and p dot m. So m will store the value of 1. K will so let's go to uh, whiteboard. So this let us define a structure P. So how this structure will work? So we have a structure P, and inside this structure we have three things. We have mass, we have spring constant, we have G, that is the gravity. So how I will store the value inside this structure? That is, I have to store the value of mass. So the way we are going to do it is P dot M equal to 1, P dot K equal to 2, say P dot G equal to 10. So when I write this thing, it automatically creates a structure like this, and it assigns a value of 1, and it assigns a value K equal to, and it assigns a value G equal to 10. So if you want to extract now, once you write this thing, you write this thing P dot M equal to 1, P dot K equal to 2, P dot, the MATLAB understands that I have to create something like this, and I have to assign M equal to 1, K equal to 2, G equal to 10. This is okay. Now, what if I want to extract this value? Now I want that my M should be 1. How I will extract this value? So how I am going to extract is, I will write M equal to P dot M. So basically this will extract this value 1. This will say that M is nothing but P dot M. So now M is simply a variable like other variables. This P is not a simple variable. This is a structure. You cannot directly use P somewhere as a variable. This is structure. And if you want this mass M, you have to extract it like this. M equal to P dot M. So if you use this and hit enter, you will see that M is equal to 1. Okay. So that is what I am using here. So where I was here? Okay. So at the top, I have already created a structure of P, and inside that P there is mass, there is K, there is G, but I want to extract those values. That is why I am saying M is equal to P dot M, G is equal to P dot G, K equal to P dot K. Okay. There is another way to do it. I could have like there is only 3 arguments for this function, that is T, Z, and P. I could use T, Z, M, G, K, L naught and give those input. But the thing is that it becomes very lengthy. Okay, this is a compact way of doing it. So okay, now this function has access to mass, this has access to gravity, this has access to K value, and this has access to L naught value. So these are available. Now I can use these things inside this function. Otherwise, if I don't extract them, I cannot use those things here. So so going backwards, what we have to calculate? We have to calculate Z dot. See here, what is Z dot? So here you can see Z dot is nothing but velocity and acceleration, Fs plus mg. Okay. Or we can say that it is acceleration in the x direction and acceleration in the y direction. So let us see what I have written. So basically Z dot is nothing but R dot and V dot. R dot and V dot, which we have seen here. So this is R dot, which is velocity, and this is V dot, which is acceleration. Okay. So I have written F dot equal to R dot V dot. But we don't know what is what this V dot and R dot is. At least I don't know, and MATLAB also don't know what this V dot is. So V dot actually is velocity, sorry, acceleration. And that acceleration is nothing but F total external, F total external force divided by the mass. So let us go here. So you can see this acceleration is nothing. This acceleration is nothing but the net external force, which is Fs plus mg divided by this mass m. Again, I am saying this that I have forgotten to write this m on the denominator. So you have to write this m here. Okay. So this v dot, which is acceleration, is nothing but F total upon m. But again, the MATLAB do not know what this F total is. So going back, I can write F total is nothing but Fs plus mg. So I am telling MATLAB that this F total which I am using, it is spring force plus gravitational force. Again, it is not knowing that what spring force is. So I am again saying, oh, this is the backward way of
It's
writing the code.
plus mg.
Yeah. Yeah, so Fs is not, sorry, Fg, that is the gravitational
Mg, sir.
force, is minus mg, but it is in the j direction, isn't it? It is in the j direction. Again, sorry, against the j direction. That is why I have used minus here. Now, this doesn't know what m is, what g is, but I have already defined those here. So m is this thing, g is this thing. But it doesn't know what j is. That is why I am writing j here. J is 0, 1. So basically, j is a unit vector. It has 0 component in the x direction and it has 1 component in the y direction. Are you getting this? This is something, if you understood this, if you understand this, you will understood this, you will understand the whole course if you understand these much amount of lines. So be sure, if you are not getting something, tell me here that I am not getting this thing, because ये कोई ऐसी चीज नहीं है जो मैं ये मान के चलूं कि आपको पहले ही से पता है. हो सकता है आप ये यूज कर रहे हो but in a different way. So I am using these things in different way. So make sure every line is clear to you.
Sir, along j, mg, mg is
Yeah.
in the negative y direction.
Yeah.
So you are taking that, sir, component of mg along y-axis is 0, but I is equal to 1.01. Why, sir, 1.01 column 0?
Why? So I use a unit vector which is along x-axis, isn't it?
Yes, sir.
I is a unit vector which is along x-axis. So first component represents the component along x-axis. So obviously the unit vector has component 1 along the x-axis, that is 1. And it has 0 along the y-axis, that is what I have written 0. Okay. Is it clear?
Okay, okay.
Okay, so these are the two unit vectors I have used because we are working in two-dimensional thing. So I have used ij. When we will shift towards three-dimensional, I will use ij and k. So okay, so we have back propagated and we have reached till this fg. So everything till now, whatever I need for the coding, I am just typing that in the upward direction. Okay. So now Fs, that is spring force. We know that spring force is nothing but minus k times L minus L naught R divided by L. So I have taken this from here. So Fs, which is a vector form, and Fs is nothing but minus times k L minus L naught upon magnitude. This L is nothing but the magnitude of R and this R vector. Okay. So I am typing this equation here. Minus k star means multiple L. My L means the magnitude of this R. Minus L naught initial length into R. R is a position vector at any time t divided by L. See, MATLAB doesn't know what is L, what is L naught, what is R, what is. So you have to tell him what L is. So L is nothing but the norm of R. See here, L is nothing but the norm of R. And L naught I have defined here. So L naught is also there. And R he doesn't know. Okay, so basically till now the MATLAB doesn't know what R is. L, it knows it is norm of R, but R, it doesn't know what it is. So we are defining R here. So what is R? So R is the 1, 2. Okay, let me do something here in order to make it clear. Okay, so let's use CLC and enter. Okay, so everything has this set. So let us take Z equal to so we know Z is something having 4 rows. So I will create a Z vector 1, 5, sorry, 1, 5, 6, and say 10. Okay, so you can see a vector. Okay, now I have to create 6. Okay, someone is waiting. Shah Salik. Hello, Ji. Shah Salik. Hello. I think he is seeing whether we are working in a good way or we are cheating here. Okay, let us continue. I'm just joking. This not a part. Okay. So we have created okay. So see, I have created a Z vector which has 4 components: first, second, third, and fourth. But if you remember correctly, what this Z was, see, this Z was R and V, and R had 2 components, X, Y, and V had 2 components, Vx, Vy. So basically, the first component of the Z vector represents the X component of position. Second element represents the Y component of the position. And the third element represents the X component of the velocity. And the fourth component represents the Y component of the velocity. So that is if I use Z of 1, 2, 2. What this will give me? This will return me first and the second row element. I will enter. So what I have got, so where is it? Oh, I have not stored it anything. Let me store it. I will call it as R equal to. Okay. So you can see when I type R equal to Z of 1, 2, it returns me first 2 elements. And I know first 2 elements are nothing but the position. And the first element of that is represents the X component and the second represents the Y component. This is what I am using here. So if I have a Z, I am taking it as first and second row element. And first and second row element, see, I have somehow calculated Z value. You have to imagine it that we have the value of Z. That is,
Sir,
yeah.
but if our matrix is so not a column or a vector, say it's a square matrix. Well, I
Yeah.
tried doing the same. I made a matrix of random integers.
Yeah.
Was a 6 by 6, and I wrote 1:2. So it
Yeah.
just gave me back the first element 1:1 and 2:1. Sir, why does that happen?
Okay, just a minute. I couldn't get what you are saying. Let us do it here. So what you did?
Sir,
Yeah.
I wrote sir B is equal to rand
Okay,
I
B
6
equal and yeah.
rand I 6:6.
Okay, rand I 6 comma 6. Okay. Oh, this is not opening now. I don't know why this is not typing. I think this has hanged. 6. Oh, no, no, no. Sorry, and the. Okay, let us take some. You just mean that we have some. Oh, what is happening? I don't know. One. It is not taking numerical values. I don't know what has happened. Either I have to restart my MATLAB, but that will take long time. I will try again if I am able to. Okay, so it has started 1, 2, 3, 4. Let us enter and write 12, 12, 14, 15. Am I audible still? I am audible or not?
Yes, sir.
Yes, sir.
Okay. Okay. 12, 14, 11, and say 16. I am not saying why this is happening. This is hanging. Okay, 11 again. And let's copy this. And let's copy this. So we get this, which is a 4 by 4 matrix. So now what we want?
Sir,
Hello?
R1, B1, comma 1:2.
1:2. Okay, so let us take EE equal to B of 1, 1,
1,
hmm,
2,
1
colon 2,
colon 2.
colon 2. Yes, sir.
Okay, let me take colon 2. Okay, so oh, okay, so I got you. What was your point? Okay, so what it will return? Guess.
Sir, I got 1:12 in my case.
1 comma 12. 1
1
comma 12.
and 12.
Yeah, 1 and
Sir,
12.
yes, sir.
Okay, yeah. Let's see. Then I will tell. So 1 and 12. So what is it basically doing? So you are okay. I think I told you to do these things. So let's have something related. So I will write B of 1, oh, 1 comma colon. So what this will return to me? 1 comma colon.
So the
I think
first one.
Yeah.
I think, sir,
Hello.
1, 4. 1, 2, 3, 4.
So the
1, 2,
first
3,
row,
4.
the
So
first
it will
row,
return me. It will return me the first
row.
row. So let us see. Yeah. So what does this mean? If I just type 1 colon 3. 1 colon 3. Okay. So you can see first 1 colon 3 means 1, 2, 3. So now going back to this, what does this mean? B of 1 colon 2. So basically this means B of 1, B of 2. Okay. So let us type B of 1 and B of 2, and then I will tell you why it is giving you this result. Let us type B of 1, B of 1. So what will be the result? Yeah. If I
I think
just
First
write uh,
1,
1, so it will return me 1. Now if I use B of 2, what I should get?
12. 12.
12.
So why 12. Why not 2?
And logical
Yeah.
index.
Yeah, so the thing is that when the indexing, the automatic indexing by the MATLAB is downwards, it assigns this as 1, this as 2, this as 3, this as 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now you can see if I type B of 2, it will return me 12. So see, it is creating 12. Similarly, if I type, so my voice is rebounding. Can you mute yourself? Yeah. Okay. Thank you. So now see, if I type B of a 5, what should I get? I don't know what has happened to this laptop. It is not typing. Okay. B of 3. 3 is typing 6. 6 is not typing 7. So if I type B of 7, what should I get?
PF7 14, I think so.
14, because this will be 1, 2, 3, 4, 5, 6, 7. So 14, this 14 I should get. So see, this is what I am getting, 14. So basically when you are typing B of 1 to 2, where is it? Yeah, when you are typing B of 1 to 2 or something, Z of 1 to 2, it will return you the first and the second element. If you write 1 to 3, if you write 1 to 3, so if you write instead of 1 to 2, if you write 1 to 3, you should get first 3 elements, because 1 to 3, 1 colon 3 is actually 1, 2, 3. We have seen it before. 1 colon 3 is nothing but 1, 2, 3. So it is basically Z of 1, Z of 2, and Z of 3. Then is it clear now?
Yes, sir.
Okay. So in Z, Z is not a matrix, it is just a vector. So there is no ambiguity. It will return me the first value, then second value, then third value. Okay. So this Z is actually an instantaneous uh, value of the storing the value of the R and V. Okay. The first two elements represent the X and Y component of the position. The third and the fourth represents the X and Y component of the velocity. This is known as unpacking of position and velocity, because these were packed in Z. Position and velocity were packed in Z. Then I am using this unpacking scheme to unpack those, because I need these things. So now this R is a vector which has two components, X and Y. And I am directly using that in here as a vector, here as a, so I think everything is now there. Okay, one thing I know. So R dot is nothing but velocity. Okay, R dot. See, we started from here. Z dot equal to R dot V dot. Then I told you that V dot is nothing but F total upon M. Then I was not knowing what is F total. I told you that it is Fs plus Fg. Fs was this, Fg was this, and L was this, R was this. Okay, everything was there. And now coming back to R dot is nothing but velocity, isn't it? This is by definition. And velocity
So
is
L is
nothing
equal
but, yeah,
L is equal to norm, or so is norm a function or is a
yeah,
variable?
it is an inbuilt, yeah, it is a good question. It is an inbuilt function. Okay, it is an inbuilt function. You need not to write this as a norm. You can also use, let us comment this. We can also use L is equal to under root of how we write as a SQRT, yeah, SQRT. That is square root of what? First component, that is X. X is nothing but first component of R. So I can write it as R of uh, that is first component. See, this represents the first component of R, which is X, taking its square plus There is some typing issue with my keyboard. I don't know. I have just renovated it, but still it is making troublesome. Okay, so I'm not able to type this key. Ah, yeah, it has come. Square. Okay. Square plus v square. So I can also use this thing. This is also okay. I think this is more understandable to you, because you know that L, if we have a vector R, let us go back to this whiteboard. Okay, so see, basically what we have this vector R. Okay, and we have L as nothing but mod of R, which I say as norm of R. This mod of R is nothing but its x and y component. If x and y are two components, it is nothing but under root of x square plus y square, where x is nothing in MATLAB terms, it is first component of R, and y is nothing, it is second component of R. That is what I am writing here. See, R of 1 square plus R of 2 square, and I am taking the square root of this thing. So if you are not happy with the inbuilt function of norm, you can also write this square root of this thing. Is it okay now? Yeah. Hello. Hello.
Yes, sir. Yes, sir. It is okay, sir. Now I.
Okay. So let's proceed. So let's erase this line again, because norm is something which is better. Not better. I think it is good to see. Okay. Now we have everything. So basically, if we know what is z, we can unpack this as like this, and we can calculate z dot. So from this function, we give my RHS. This is the name of the function, my RHS2, and the input to these function is that this function says, give me time, give me z value, and give me p. I will spit out the value of z dot. Okay, so whenever you give this, whenever you use this my RHS and you give it the value of t, z, and p, it will give the output as z dot. How it will give? The process goes like this. So basically, the output of this whole function is z dot. Is this okay? If there is any confusion, because this is the main thing which we will be using throughout this course. Yeah. Hello.
Okay, sir. Okay. Okay.
Okay. Dayan, it is okay? Hello? Hello?
Hello.
Dayan. Is it okay?
Sir, shouldn't we be changing that L naught value every time we calculate it? Because the new L is the new L naught in that case.
No. L naught is not something which is changing. It is the normal length of the spring, or the unstretched length of the. What is changing is L. L is every time L is changing, and what is L? It is norm of R. So L will keep on changing. L naught is something which is constant. Okay, that is why I am calling it as a parameter. L naught is the initial value. Sorry, it is not the initial value. Initial value is something different. L naught is not the initial value. L naught is the unstretched length of the spring. There is difference between initial value and the this L naught. Initial value means that maybe at t equal to 0, the spring may be stretched. So the value corresponding to the length of the spring at time t equal to 0, that is not what I am defining this L naught. L naught, I am defining it as a constant normal length of the spring, and that will not change with time. Is it okay?
Yes, sir. So
Okay, so this is a constant, one of the constants for this given system. Okay. Oh, yeah. The thing is that, yeah, the length of the spring will keep on changing, and that length is depicted by this L, which is norm of R. Okay. So from this function, I am getting now Z dot. And you know what we have to do with the Z dot? We have to integrate it. And that is why I am now using this, where I am. Okay. Oh, so see, I am using this function my RHS2, which I defined here, and which is giving me a Z dot. I am redefining another function as RHS. That is why I wrote this as my RHS, because I was knowing that I have to define another function which will be used by the ODE and which we call as RHS. And why I am defining it like this? The thing is that I have told you before, when we write this, when we define a function like this, it means that there are only two variables. What are the variables? T and Z. What were the variables here for this function, my RHS2? How many variables were there?
T, Z, P.
Yeah, T, Z, and P. So there were three variables. I have to feed three variables to this function in order it may give me the value of Z dot. But if I directly serve this to the ODE will not work. The thing is that ODE always likes, not only likes, it permits only Z and T, only two variables. So that is the reason I have changed, I have redefined my function. I have redefined my function, and I have redefined it like so that the new function is function of T and Z also only. Although there is P, but when I redefined it T as Z, it will take P as constant. It will not take P as a variable. Okay, so only variables are T and Z. Now this RHS function, it is a new function. It is a new function, and it will take T and Z as the variables, and obviously it is also giving me the Z dot value, because my RHS is giving me Z dot value. So this function will give the Z dot value. And we are giving that Z dot value to ODE here. See, I am feeding this. And this ODE will integrate this. I am using tspan for which I want this integration to be taken. And Z naught, that is the what are the initial conditions. And I am using options to control my error. I will talk about this someday if I get time about this option. Basically, it is, I think, enough if you think that it controls your error. We may change these values, and you can see how the solution changes. Okay, and the rest of the things are same. Once you get the solution, and then you define your time, and then you get Z value. See, here this RHS is nothing but it is Z dot, and OD is integrating that Z dot, and integrating Z dot will give Z value. So basically the solution is nothing but the Z value, and that is what I am taking here. Z equal to devolve solution T. If someone has not attended the last time, I would highly recommend to go through that lecture, so that you will understand what I mean by these three lines. Okay, what is happening in these two or three lines, you will understand from the last lecture. Okay, once we get the Z value, which in itself contains X, Y, and Vx, Vy, we are unpacking these things. We are taking X as Z of 1. Basically, now this Z is not something 4x1 vector. This is actually a matrix which is storing 4x 4x 1000. It is a 4x 1000 matrix. Okay, this Z, whose first row represents the X component position at different times. So this X is not basically a single value, it is a row vector. So there will be 1000 values of X. First value represents the position, X position at t equal to 0, and then t equal to t1, t2, t3 up to t1000. Similarly, y, similarly, vx, v. So vx, z. So 1 comma colon, it will give me the whole this row. You can see from here also, this x is 1 cross 1000. So it is a row which is storing 1000 values. Y is also a row which is storing 1000 values. Vx is also a row which is storing 1000. Vy is storing 1000. Okay. So okay, so this xmin and xmax are something which are related to axis. I will, because see, I am skipping lot of things because I know I have to repeat these things so many times, and discussing all the things in one go, it will create confusions and nothing else. So you have to bear with me, maybe few more lectures till you know everything about this, what I am writing. Okay, so now we get x, y, and vx, vy. Now we need to plot xy. So we now plot how x and y varies. Okay, so that is something here. And then we want to animate this thing. I have done these things in previous lecture. That is why I am going fast in these lines. See, this is I start a clock. I initiate the new timing. Then I want to plot this. See, our particle is at x naught and y naught, and x naught is nothing but the r naught's first component, and r naught second component is y naught. Then I need to draw its trajectory. For that, I start it from the initial position. I want to plot my spring. For spring, I am using this thing. Okay, let us animate, and then we will see how things are going. So let's run this and see if it works good. Okay, so I think it is running good. So there was a question from someone. Okay, or what we know. Let us take this g equal to 0. What does this mean?
There is no component along the gravity.
So there is no gravity. There is no gravity. See, you have a spring. You have a spring here, and there is nothing which is pulling it down. Only thing, if you if you elongate it, it will come back and oscillate, isn't it?
Yes,
It
sir.
will oscillate.
Oscillate
Is it
in
true?
XY plane.
Can anybody guess? Can anybody guess what will happen if g is 0? What will be the kind of the motion?
That it will stay there.
It will stay there. Okay. Why it will stay there?
That there is nothing to force it. And if initially L is equal to L naught, there is no spring force as well. Or if
Okay, so
there is between unstretched and this, it will move towards the origin only and oscillate along that.
okay. So, but we have not put any condition, initial condition that initially it is in normal position. So your second argument is right that if it is not in the if it is not in unstretched condition, that then it will oscillate. Okay, I'm not saying that this is correct, but at least you have pointed out the difference between the two. That is, if it is at the normal position, that it will stay there. But if it is perturbated, then it will start oscillating. I don't know whether your answer, I know obviously, but I mean,
So
uh,
when I say
yeah.
alignment along, if it isn't, if it's still perturbated at an inclination, it will still stay there. only if
Yeah.
L is equal to L naught.
Yeah. And if it is disturbed, then it will oscillate. That is what I am saying. That also I don't know whether that is correct, because you are saying that it will oscillate towards the origin. So let us see if your argument is correct, and if it is correct, how much it is correct, and if it is wrong, how much it is wrong. Okay, let us see. So yeah. 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 So are you correct? Yeah, you can see it is oscillating.
Yes, sir.
Yeah. A nice animation.
Yes, sir.
Is so I want you to be able to animate everything, and the animation should be very nice looking. Okay, when you keep playing with these coding and other things, you will get to know that how things are changing, and how what programming line is telling me what it is doing, what is the purpose of that line. You will get to know these things only if you play with these coding lines and other things. Okay, so okay, so you have predicted that if there is no if there is no this no gravity, it will oscillate, and it will oscillate through the origin. Okay, so let us so we have, I think we are running short of the time. You also when the class is running, I don't remember about the finishing up class, because I get too much involved in the lecture. So you should also sometimes tell that time is running out. We have some else to do. So it is not something which is offensive. I will take it easy. But if you want to, sometimes we can have 5 or 10 minutes more. That is also okay. But see, this animation, there is lot you can do. You can keep changing on these values, and there is lot of information. I can just say it will take you, if you play with these equations for whole week, every time you will get something new. I can tell you for sure. Every time you will get new. But thing is how much you are playing. See, I have put the initial condition on the on this R naught. Let me put initial condition on this velocity, and let me see what will happen. 0.3, and then we will close. Okay, what happened? Mm, something is wrong with this keyboard. 0.3. Let us take. See what this basically mean, that I am releasing it from 10 comma 5, that is okay, but I am giving it an initial velocity of 0.3 in the y direction. So let us see how the spring will behave, spring mass system will behave. Okay, yeah, see, are you getting? See, there is no gravity. You can imagine this thing, there is no gravity, yet it is not oscillating through origin. And I think some nice picture is coming. You see, you have to analyze these things, because it will take me months if I keep analyzing everything. Okay, so it is your duty to keep changing on parameters, to keep changing on initial conditions, and it will also make you understand how much initial conditions are important. Till now you just see them as constant values being put in the differential equation, but now the things will change once you start analyzing these things in the simulation. So basically what simulation serves you, it it like if you want to do this experiment, you have to put whole setup and then do these things. but in simulation you can create anything. That is the whole purpose of doing this course. I am not saying that you will learn much of the new dynamic problems, but at least this will create something in you that you will try to uh, animate everything. That is the purpose of this course. Obviously, you will also learn much about the dynamics. That is also a point here. But the main theme of this course, the main motive of this course is that you should be able to use your computer to solve the dynamic problem. So, any question? So I would like that you, okay, one more time because it is being recorded. I will go through whole of this coding. I will make it visible so that when you go back, you are able to type these. Uh, if anything is not visible, make sure that you point it out.
Do you recommend any physics engines which we can use to validate our results? If we write something and if we want to see if it's correct or not,
Yeah,
are
you
any simple engines
you
available?
you have raised a good question. So everything is visible till now. Whatever code I just scroll down and up. Yeah, I think everything was there. So now coming to your question. So you are saying that how do we know whatever we are doing, is it correct or not? So inshallah in the next lecture we will be doing something like that. How we can evaluate our solution, whether the solution is correct. Because if MATLAB gets some X and Y input, it will generate this animation, and that doesn't mean that your solution is correct. Okay. So there are ways to evaluate our solution. I will not recommend anything to you that you do. Those are very simple things. You have to understand those things. Inshallah, we will be doing that in the next lecture. Any more questions?
There's still any engine you recommend to use for
Yeah,
this
I have
part?
already. I think I have in the syllabus copy. I have recommended some books there. You can refer to those books. They are already there, and most of my content will be from those books. Yeah. Anything more? Yeah.
No, sir.
Okay. When you go back, see, make sure that you understand every line and everything you understand. If you have any question, please let me know that in the next lecture or maybe in between these days, you can call me or you can write me via email. So but make sure that you understand everything, because as we are going through the course, the more and more difficult problems will be solved. So I want to make it sure that you understand all these coding and other things. If there is no question, I think we should call it a day. Yeah.
Yes, sir.
Okay, thank you for your patience of listening. Thank you. You can leave now.